Hi guys, welcome back to my channel. So in this video we're gonna learn about the ionization potential. So now let's get started. The ionization potential is nothing but the minimum amount of energy required to remove an electron from a gaseous isolated atom. We can write the definition as the minimum amount of energy required to remove an electron from the outermost shell of an isolated gaseous atom. Ionization potential always needs energy to remove an electron. So it is always endothermic process. It is always an endothermic process. And it is measured in electron volt per atom or kilojoule per mole or kilocalorie per mole. And another important point is energy required to remove an electron from unit positive gaseous ion to convert it into dipositive ion is called IP2. So energy required to remove an electron from unit positive charge into dipositive ion is called IP2. So we can represent it as Mg plus IP2 gives rise to M2 plus electron. And in the same way, energy required to remove an electron from dipositive gaseous ion to convert into tripositive ion is called IP3. We can represent it as M2 plus IP3 gives rise to M3 plus The next topic is factors affecting the ionization energy. And the first factor is atomic size. Next one is nuclear charge, screening effect, and the last one is electronic configuration. Here is the periodic table, and now we're gonna learn about the variations of ionization potential in groups and periods. The ionization potential decreases down the group due to decrease in nuclear charge and increase in atomic size. But across a period, the ionization potential increases due to increase in nuclear charge and decrease in atomic size. So we know that across the period, the atomic radius of the elements decreases. So if we take the example of the second period elements, that is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So here, as we move across the period, the atomic radius decreases. So the atomic radius decreases due to increase in the nuclear charge. So if the nuclear charge is more, the IP will be more, because the removal of electron will be difficult. But whereas down the group, the atomic radius increases due to decrease in the nuclear charge. So if you take the example of 1A group, lithium, sodium, potassium, rubidium, cesium. So as the atomic radius increases, the removal of electron will be easier because the nuclear charge will be less. So if the removal of electron is easy, the IP will be less. So down the group, the IP decreases, but across the period, the IP increases due to increase in nuclear charge. So with this, we can just give a conclusion like IP is directly proportional to nuclear charge, and IP is inversely proportional to atomic radius, atomic size or atomic radius. The next factor on which IP depends is electronic configuration. So if you see, s orbital is more close to the nucleus than any other orbital, and next orbital which is close is p orbital, and next one is d, and next one is f. So as the orbitals are more closer to the nucleus, they get attracted towards it, and the removal of electron from that orbital will be more harder. So as s is more closer to the nucleus, the removal of electron from s orbital is more harder than p orbital. In the same way, the removal of electron from the p orbital will be more harder than the removal of electron from d orbital. So we can just say that IP will be more for the s orbital, and next one will be p, next one will be d, and next one will be f. So we can just write as s, p, d, f, decreasing order of IP. The important point is, as positive charge increases, IP increases, but as negative charge increases, IP decreases. Because it is very difficult to remove the electron from the cation, but whereas it is very easy to remove the electron from the anion, because already the electron is added, and it is very easy to remove the electron again. And hence we can say that IP is proportional, directly proportional to positive charge, and IP is inversely proportional to negative charge. So here the noble gases have the highest IP, but whereas the 1A group elements, that is alkali elements, have the least IP, because the atomic radius for 1A group elements is highest. As IP is inversely proportional to atomic radius, the IP1 for the alkali metals is more. And I forgot to tell one thing, that is IP1 is always less than IP2, less than IP3, and so on up to IPN. In all available elements, helium has the highest IP1 and cesium has the lowest IP1. Helium has the highest IP1 in whole periodic table. Cesium has the lowest IP1 in whole periodic table. And we know that IP1 decreases across the period, but actually there are some exemptions for which we'll learn now. So if you see second A group elements like beryllium, magnesium, etc. If you see beryllium, atomic number is 4. This is 12. Electronic configuration of beryllium is 1s2, 2s2. And for magnesium, 1s2, 2s2, 2p6 and 3s2. So actually s orbital is completely filled. In the beryllium and magnesium cases, like secondary group case, the s orbital will be completely filled. So as it is completely filled, the removal of electron from this will be harder. That's the reason why the removal of electron from the noble gases is more harder. Like if you see in the neon, it has 1s2, 2s2, 2p6. One s2, 2s2, 2p6. Actually, this is completely filled. Actually, so because of this, as it is completely filled, the removal of electron from this will be harder. So the removal of electron from this s orbital will also be harder. So the IP1 for second A group is greater than IP1 for third A group. And another exemptional case is fifth A group elements. So if you take examples like nitrogen, phosphorus, etc. In the case of nitrogen, like atomic number is 7, 1s2, 2s2, 2p3. It has symmetric electronic configuration, that is half filled electronic configuration. P orbital is half filled. So as it is half filled, the removal of electrons from this p orbital will be harder. So the IP1 for 5A group elements is greater than IP1 for 6th A group. These are the two exemptional cases in the IP. And that is the reason why the IP1 for nitrogen is greater than IP1 for oxygen, and IP1 for magnesium is greater than IP1 of aluminium. So we can just write the order of IP1 as 1A group as least, next will come the third A group, next is second, next is fourth, next is sixth group, next is fifth group, next is seventh group, and the last one is eighth group. And 0 group elements have highest IP. So just we can arrange them in the increasing order of IP. So here actually this is in the group, it is down the group. So down the group the atomic radius increases, IP decreases. So lithium has greater IP than Na, Ka, rubidium and cesium. This will be the order of IP. Increasing order of IP1. And the next is across the period. So across the period the IP increases. And here we have an exemptional case, that is second A group, Mg and phosphorus also. So the order will be like lithium less than, aluminium less than, Mg less than, silicon less than, sulfur less than, phosphorus less than, chlorine less than, argon. Increasing order of IP1. Across a period. And now we'll just take a small example like lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And down the group. So the increasing order of IP is, we'll first take the group. So across the group, that is down the group, the IP decreases and the atomic radius increases. So lithium has the greatest IP in 1A group. This is decreasing order of IP1. And now we'll just do across the period. So across the period, actually the IP increases, but there are some exemption cases which I have told for second A group and fifth A group. So the order will be this is the order for IP1, but the IP2 order will be different. Now for the same elements we can just write the IP2 also, like IP1 for lithium, beryllium, boron will come, beryllium, then after carbon, then after oxygen, then after nitrogen, fluorine, next is neon. But for IP2 it differs. It will just become less than neon. And the 1A group elements, the IP2 for 1A group elements will be the highest. That important point. IP2 for 1A group elements is highest. Thanks for watching this video. Please do like, share, comment and subscribe to my channel, and please do click on the bell icon for more updates. And in the next video we're gonna learn about electronic affinity. Till then, bye bye.